I think I started streaming in the wrong thing. Let's see if it's okay now. Should be. Yeah. Okay. YouTube's working. LinkedIn working? Yes. Okay. Cool. All right. Hello, everybody. Welcome back. Happy start of the week. Happy Monday. Today I'm sipping some iced mocha cappuccino like protein shake. Pretty good. Welcome back. So this happened. That's kind of crazy. I mean, okay. So this weekend was World Cup games were kind of crazy. Like the France England game, I didn't get to watch it. I was a little bit busy, but I was checking in on the score, and I'm like, okay, let's check in at halftime. I check in at halftime, England 4-0. I'm like, okay, I guess. Just I guess just don't care. You just ball. And then I check in at like at the end of the game. I'm like 6-4. Okay, just Mbappe locked in, I guess. It must have been a crazy game. I need to watch like the highlights. But I did watch the final World Cup game, the Argentina-Spain, and that was pretty good. But okay, no, I'm not gonna say it's pretty good. It was honestly kind of boring for like the first 70 minutes. Like Argentina, I think they got like 2 shots, none of them on target. Like whole time, they got like 9 yellow cards. They like flipped this one whole guy from Spain just like a Ferris wheel. He just went flying. It was like a rag doll, pretty much. It was kind of funny. And yeah, Spain just kind of scored, and then they got 1 goal canceled, which was kind of a little bit BS. But yeah, congratulations Spain for winning the World Cup. I mean, I wasn't cheering for either of them. All the teams that I was cheering for were like gone out of the World Cup by the time but like for like the finals. But I was like, not Argentina again. Like, let's try something new. At least Spain hasn't won since like, I don't know, what is it, like 2000? When did Spain? (2010). So yeah, 2010. So it's been 16 years. They deserved another one. They played like they got 1 goal against the whole time by like Belgium. But they won every single match. Well, no, they tied against Cabo Verde. They got 1 goal against the whole time. They played pretty well. Deserved. Definitely deserved. All right, that's enough football for today. This is not a football channel. Okay, so today we're gonna keep doing some LeetCode. This week, if you've seen my socials, I'm doing a lot of streams. I'm doing 4 streams. I need like 1 each day from today until Thursday. Just gonna have some extra time on my schedule, and I felt like it. I want to really advance on the C# project, because I need to like get up and running and learning a lot. So yeah, it's gonna be a good chance for that. But today we're doing LeetCode. Today we're starting the week simple and easy. But to start, let's go ahead and do the Lorcana card of the day. And another cool announcement is that the new set for Lorcana came out. So if we go to Dreamborn, these are the cards from the new set. Let me just filter to Attack of the Vine. And I think the entries Turning Red and Up are the new cards, like the new franchises that are coming into Lorcana. Didn't watch Turning Red, but it looks, I guess, interesting. It's kind of like Hulk kind of thing. But I really want you guys to look at the enchanted cards, like the special rarities. Like these are like okay. This one's kind of cool. This one's really cool. But if you keep scrolling down, there's the enchanteds, and the enchanteds look amazing. All the enchanteds for like this set look really good. Like this one is really nice, and look at the prices too. I mean, it's like pre-release prices, like they'll come down eventually, but like they're kind of crazy art. Is there Ian McDonald ones? Ian can no Ian McDonald. Okay. This one's really cool. This one's really cool. The one I like the most is I think the Scar one. I think people don't. I've heard like today, like this weekend I went to play at my local game store and I heard people didn't like this one. I think it's really cool. And then these are the iconics, which I mean this one's really cool, but like this one's kind of eh. I don't like it that much. But maybe it looks better like the physical card. But really good enchanters overall. And I just added them to the Lorcana Card of the Day script, so it might pop up today. Maybe. We'll see. It did not. So we're getting a set 10 card. So this is our Lorcana Card of the Day. It's called The Twins Lost Boys. It's a 6-cost inkable card. It costs, it has 5 strength and 5 willpower. It's a Storyborn ally, and it says 2 for 1. When you play this character, if you have a location in play, you may deal 2 damage to chosen character. And a quest for 2. It's by artist Hannah Augustine, and it's card 186 out of 204 of set 10 in English. It's a common. This is bad. Honestly, not good like at all. Like, stat line is kind of bad for a 6 cost. I know it has like this whole effect, but you need a location in play, right? This is our steel card. It's called Vincenzo. Yeah, look at this. Compare these two. So, okay, the strength here is just 2, which is fine, but it has 8 willpower, which is a lot. It costs only 1 more. It quests for 3, and when you play it, you may deal 3 damage to chosen character. This is so much better than this. Like, you don't need to have a location in play, you deal 3 damage, you quest for 3, you have 8 willpower, and it's only 1 more. Yeah, the 5/5 quest line, like the 5/5 stat line is not great. This effect is not great. The cost is not great for this. So it's a bad card in general. I think this is from Peter Pan, maybe. Yeah, it's from Peter Pan. But yeah, nope, not a good card. Anywho, let's go into Grand 75. Okay, so we did threesome last, which was kind of fun. And now we're doing binary tree level order traversal. No. Yeah, we finished this one last time, I just didn't click it. We are doing clone graph and evaluate reverse polish notation. So let's do clone graph. Okay, so I don't, as I've mentioned before, I don't solve the problems before the stream. Like, I leave it for the stream for me to solve live because I feel like it would be kind of disingenuous if I solved them before and then just gave you the solution. However, I do look through them before, like when I'm planning the stream, for a couple of reasons. First of all, to put it in the description, because I put in the description which problems I'm solving for the day. And then also to get an idea of like the difficulty of the problem and start getting ideas on how to solve it. But I don't go into the full implementation yet, and I don't look up solutions. Everything I'm doing here are solutions that like I've either come up with in the past that I remember, or like I just figured it out because like of experience in pattern recognition, but I don't look up solutions for these. It's like, once again, like same as last time, it's a solved, but it's from, I solved it in November 2024. So it's been a while since I solved it last. Um, and this is it's a medium. It's kind of a weird problem, I thought at least. And it says, given a reference of a node in a connected undirected graph. I don't know why they just, yeah, connected. Oh, I think connected graph is that, like, you don't have any disconnected nodes. Like, all of them have to be connected by an edge. And like you don't have like two like graphs separate from one another. And it's undirected, so the edges go both ways. Return a deep copy of the graph. Each node in the graph contains a value and a list of its neighbors, like this. And then this is just like some formatting for like the test input, but like you're actually like reading the you're reading the input, like the data structure you get is this. You get a couple constructors and stuff. But you're supposed to do a deep copy. So in case you don't know, what is a deep copy? A deep copy means, okay, so these, once again, these are classes, or like it's a like a structure. It used to be in C. This is a class, and so classes, the way they work is you get, when you create a class, you get a pointer to that class, and that pointer is gonna have all of your data. You're gonna have like you have like a link to all of your data. So you don't actually, like, when you put a class into a variable, when you instantiate an object, it's not like you're putting the actual object there. You're creating the object, and then your variable contains a pointer to that object. So when we're saying a deep copy, it means that, like, if I want to copy this graph, I can't just return the same graph. So like I can't just like copy the pointers themselves. I have to create a new object, copy all of the information over, and then return it. And like, I mean, it sounds kind of complicated. I don't know if there's like a drawing for this, but okay, let's draw it. Let's draw memory. And so imagine you create an object. In this case, it's a node. So what's gonna happen is you create the object, and so like these are your this is your memory in your computer, and it's just like divided into pieces. And so our node contains like a value, a list of neighbors, and a list of neighbors. A value and neighbors. So to store this, what's gonna happen when you instantiate an object is it's gonna put these values in here. So it's gonna, let's say a value fits in like this much memory, and then the neighbors, let's say they fit in like this much memory. Like these are the neighbors. Sorry, maybe I'll do val and then neighbors. Like these are the neighbors. So this whole thing is gonna be your object. So let's call it node, or n1. This is your object. So it's gonna put all of this information here, and then when you instantiate it, let's say you called your variable n1 is equal to like your object and your new node. What's gonna happen is n1 is not gonna be this whole thing. N1 is actually just gonna be a pointer that like points to this memory address. And it has some information about like how to access, well, like your compiler figures out how to access the different parts of the object, but it doesn't actually store the whole thing. It stores a pointer to the beginning. So let's say we only have one node and we're trying to make a copy. There's what do you call it? A soft copy. It's not a soft copy, it's a shallow copy. Yeah, you have a shallow copy. So what would that be? I tell you, give me a copy of this, and so what you do is you create a new pointer. N2 is going to be equal to N1. So what's going to happen is this new pointer is just going to point here. So that's your shallow copy. It's actually the same information. So if I say N2 dot val is equal to 6, then n1 dot val, like let's say like the val here was 5, and then you change it to 6, then n2 dot val is going to be equal to 6, and also n1 val is going to be equal to 6. You're going to modify both because they point to the same reference. That's a shallow copy. Now, with a deep copy, what happens instead is, instead of saying n2 equals n1, you create a new node, just an empty node. And then let's say that gets stored. I'm going to need one more here. So val, let's just say val1, val1 and neighbors 1, I guess. And then this is val2 and neighbors 2. So you create these with like empty values. So let's say this would be 0 and this would be an empty list. And then if this value here was 3, what you're gonna do is it's gonna be n2 val equals n1 val. So now you've copied the 3 here. And now instead of doing n2 neighbors equals n1 neighbors, you can't do that because then you're doing a shallow copy of the neighbors and you need a deep copy of the neighbors. So what you're going to do instead is for each neighbor 1, I'm just going to call it neigh1, we're going to say n2 neighbors, I'm just gonna call it neigh, dot pushback or append, or let's call it just push, push the, like a copy of neigh. Well, in this case it would be a new node that's a deep copy of neigh. So it's like here there is some like recursion a little bit. I don't know if I can explain like the whole implementation through like a drawing. I think it might be best if I just start doing it and explain it as I go. I think is what would work best. But what would happen here is like you create a new node. You don't like fully like instantiate it yet. You just put it with like default values. And then on the next iteration, you go over this node and then fill it up with the values it needs, or like fill up the neighbors, because the thing you can fill up with the value itself. This, so let's say it's like a 5. You can do that. Well, in this case, it would be neigh.val or whatever. But then for the neighbors, you need to actually go into this node, visit all the neighbors, and then create them. And there's another caveat, and that is, okay, this is hard to explain. You have your graph, right? Let's say it's this graph. Now, you create one, and then you go and create 3. So you create 1, and then you create all of the neighbors. So you create 2 and 3, and then you go to 2, and then you go and create the neighbors of 2, and then if you're doing it naively, it might just like create another 3, and you don't want to do that. You don't want to create duplicate nodes. So you have to check, have I already created this node before? And if so, instead of creating a new one, just point it to the correct one. And we're gonna just keep track of the nodes we've created in some sort of array. But yeah, this is a little bit hard to explain. If you have any questions, just send them in the chat. I'll try to answer them, but I'm gonna try to explain it as I code it up. Okay, so let's grab this. And so this is a graph. It's a graph problem, I guess, because it's a graph, but I don't know. I don't really think it's a graph problem. I guess it helps you like navigate through graphs. League of Legends. Okay. So do I have graph? I do. And then graph, and then 133.cpp. Okay. So okay. Can I do this recursively? Yes, I can. Let's do it recursively because it reduces the complexity a little bit. But what's gonna happen? I might need to create like a helper function, but it's gonna be the same thing basically. So we're gonna call it clone recursive, and it's gonna be the same signature basically. That was the other function. Okay. And what we're gonna do is we're gonna return clone recursive of node. And then up here, we're gonna have some sort of way to keep track of which ones we've done, which ones we haven't. So if you see here, it says the number of nodes in the graph is from range 0 to 100, and each value is unique. So that's how we're gonna keep track of which ones we've done. Which is basically by creating an array. So done nodes, I guess. Or we can be a bool. It can be a bool, so we're saving memory here. So bool node done of 100. The numbers, let's do 101, so we're just doing one extra element, it doesn't matter. Okay. So every time it calls this function, which is the solution function, we're gonna clear that. So for int I equals 0, I less than or equal to 100, I plus plus. We're gonna say node done, I is gonna equal to false. We're just gonna reset the array because it calls the same function, and if we don't clear it over different test cases, it's gonna keep the same information, and we don't want to do that. Oh, actually, this does not suffice because we need a reference to the node we've created in the past. So this is actually gonna be that. So it's gonna start, I think it starts this whole thing as null. So node done I is not gonna be equal to false, it's gonna be equal to null. Or is it null PTR? Okay. So this is basically resetting it. And this should be 101 still. Okay. So here on clone recursive, okay, so what we're gonna do is every time we get a node, the node should already be instantiated with the value it needs. How do you get a reference to the node you need to clone? We need like a current pointer. So, okay. we're gonna create a node current pointer is gonna be equal to new node, and the value is gonna be node val. And then here we're just gonna instantiate the neighbors. So we're gonna pass it the current node and the node you need to clone is what this function is gonna receive. So node per and then the node you need to clone. Okay. So the value, okay, to make it simple, let's not instantiate, just create a new node like this. Do you return just any point in the graph? Oh, copy of the given node. I think that's fine. Okay, so do that, and then because it's gonna modify cur. Which we can just make a copy and then pass that. Yeah, no, that's fine. Okay, so right here, we're gonna say our current node, which should be already be created. Okay, first of all, if node is null, then we return node. That's it. Just to say from like edge cases. Now here, cur val is gonna be equal to node val, and then for node n yeah, it's gonna n of node neighbors. So this is just a copy of the pointer. What is gonna happen here is we're gonna clone recursive. It's a vector. Okay. So we're gonna say, is there an, okay, for vector, is there an access to like the last element? Begin, end. I guess you could do end. What are the element at, front, back? Access the last element. Okay, so back. I've never used back in my life, but this is gonna be the first time. So our cur neighbors dot pushback new node. We're gonna create a new node at the end, which is going to be the one we're gonna copy. Or I guess if this is returning a node, then we don't really need to do this. I think we, no, we don't need the cur even, I don't think. I feel like I'm optimizing a lot here that I don't need to, but basically here you create node per equals new node. We can do node val here. Now we can delete this. And then for each node in node.neighbors, cur.pushback. Oh, actually, cur neighbors dot pushback clone recursive of n, right? And then at the end we just return cur. Now there's one thing here, this is what I mentioned at the beginning, and is if the node's already created, then we don't create it, we just return it. So instead of creating it here, if node val if node done of node val, if we've already done this node, then we don't need to create it again. Then we just return node done of node val. We just return it because we've already created it. Otherwise, we create it, we iterate over its neighbors, and then here we say node done of cur val is going to be equal to cur, and then we return it. We should probably do that up here before we do over the neighbors. Because that way if we find it again while we're recursing, then we don't go into this again. Okay. This looks decently right. Now I think that I have a better picture. I think I can draw it. So, we have our graph. We'll do like a very simple graph here. We'll do that, and then we'll do that, and then another node here. So it's 1, 2, 3, 4. So this is this is the original graph, OG, and then this is gonna be the clone. So, at first, and then let's create here node done, and then do that. Yeah, there's just gonna be, let's say 1, 2, 3, 4. So I'm just gonna skip 1, and then these are empty for now. So we're gonna start here, right? And what it's gonna do is it checks, is it done? Is 1 done? No. Since it's not done, let's create it. Let's create 1. Now, after we've created 1, 1 is done. So I'm just gonna do an X there. That means it's done. Next, let's look at its neighbors. So starting with 2. Let's say 2 is the next neighbor. So it goes into no recursive for 2. Clone recursive, and then we do the neighbor, which would be 2 in this case. So we're gonna go into 2 here. Then it checks, is 2 here, is 2 done? Then it goes and checks, nope, 2 is not done, so let's create 2. And now 2 is done, we mark it off. And now let's go over all of our neighbors, which are 3 and 4 and 1. So here it would go to 1 first. It would go to 1 first. If we do it by like order of numbers, it would go to 1 first, and then it would say, it would go back here, and here would check, is 1 done? Yes, then it will return. It would go to its next neighbor, which is 3. So now we clone recursive 3. So then we go to 3, and then it says, is 3 done? No. Well, let's create it, and let's go over all its neighbors. Oh. there's a problem here, I see. And that is, we're gonna create two links for the same, like in this case in one, there's already a link from 1 to 2. Yeah, but it's a double link. So I think that's fine. Let's keep so far it's fine because at first we created a link here and now we're creating a link here, so this link is complete. Now we're at 3. So we've actually so far we've only created the link here because we haven't finished the thing. So we go to 3, we create it, and then we mark this off, and then we check all of its neighbors. So starting with 1. So we go to 1. Does 1 already exist? Yes. If so, return it. So now we have a link like that. And now we go back to 3. Then we check 2. Does 2 already exist? Yes. If so, return it. Then we're pointing here. And then 3 has no more neighbors. Then it returns here. It creates this pointer right here. And then, so it's done 1, 3. We're iterating 2 right now. So now it goes to 4. So it says, have we created 4? No. So then let's create it. And then we go over all of the neighbors of 4, which there's only 1. It's 2. Is 2 already created? Yes. If so, we create this link here. And then we go back. Since this node is already created, then this link is created. And then we go back to 1. And then it creates this link right here. And then now 1 is going to check for 3. See that 3 is already created. And then it's just going to return immediately. And it's going to make this link here. And now we have everything connected. So it should work. It's just, okay, the problem's not that complicated. It's just kind of hard to, like, explain. Kind of hard to put into words. User is not authenticated. Excuse me? Oh, I guess. My Gmail. Okay. Paste. Test. It works for the 3 test cases, and I'm hoping, and I'm pretty sure it's gonna work for the final solution. Yes, it does. Speeds 68% in runtime and 82% in memory. Cool. You know, after doing, well, I'm not gonna say a lot because I feel like there's a lot of people that have done a lot more problems than I have. But after doing some of these, I feel like I'm getting better at finding edge cases because I was really bad at finding edge. I mean, not that it matters a lot with like LeetCode, but finding edge cases. I used to be like, oh, I code my first solution, and then if it doesn't have a compilation error, I just send it without thinking about like edge cases. And like that's fine because with LeetCode you can just, there's no punishment for you to submit a lot except that you might have to wait a little bit more. But it definitely matters for things like contests, like Codeforces, like competitive programming contests, like Codeforces contests, or like LeetCode contests, where you get like a punishment for submitting, like you get like a cooldown or you get minus points for submitting incorrect solutions. So it's important to look at your assumptions and your edge cases. And then also, I mean, it's also important for the interview because it kind of shows that you're able to think about how your program could fail and you're not just like sending whatever code you find first and then just testing in prod kind of thing. So I think it's a good skill. And what comes into this is actually talking through the solution and drawing it out kind of helps me a lot because going through like an example, like in a small example like I showed, you find those edge cases naturally, and then when you find them naturally, you just start thinking about them before you even draw it. So it just kind of comes as like you do this problem. So I would recommend maybe not do a stream if you don't feel like it, but practice solving interview problems and like talking through your approach, um, because that helps you with your thought process and with your solution process, when you're actually in the interview. Okay, but cool, we solved this one. Go to here, clone graph, done. Evaluate reverse polish notation. Okay, I also remember this one. This one I last solved in November 6, 2024. I was grinding out these problems in November 2024. All right. So let's go to this one. And now it says 150, evaluate reverse Polish notation. You were given an array of strings, tokens, that represent an arithmetic expression in reverse Polish notation. We can check this, but I think what's most useful is just to go through the examples. Evaluate the expression. Return an integer that represents the value of the expression. Note that the valid operators are addition, subtraction, multiplication, and division. Each operand may be an integer or another expression. This part is important. The division between two integers always truncates towards 0. So just use your regular int division. It'll be fun. There would not be any division by 0. They kind of take a little bit off our plate here. The input represents a valid arithmetic expression in reverse Polish notation. That's assumed. And the answer on all intermediate calculations can be represented in 32-bit integer, so we don't have to worry about floats and stuff like that. So here, so the way it works is, so you have your tokens and you read them from left to right. So here you're given a number 2, you're given a number 1, and then you're given a plus. Whenever you're given one of these operators, you take the two parts that you had left before. I'm not going to say the two numbers because they can be expressions, and you do that operation for the previous numbers. So if we get 2, 1, and then the plus, that means we add the previous 2, which are 2 and 1, and that gives us 3. And now think about it like this. You have a left and a right. Okay, let's actually do this. Okay. Let me copy this. Okay, we're gonna copy it again. Okay, so think about it like this. You have 3 important parts. You have your left operand, your right operand, and your operator. And now you start filling those values from left to right. So here you get 2, then you get 1, and then you get plus. So now you do the operations because you have all 3. 2 plus 1 is 3. So that solution is going to go into our left operand. Now we get 3 in our right operand, and we get our multiplication. So we're going to do the operation. 3 times 3 is 9, and that's going to go in our left. And since there's no more operations, we just flush this out, and this is our solution. Okay, pretty simple. Let's look at a more complicated example. Can I... Okay, I'm just gonna paste it on top. There we go. Now, this is a little bit more complicated. Because you do... So it's not exactly left, right, and operand, but this is a way of simplifying how to read this. But you basically take the previous 2. So here you would go 4, then you would go 13, and then you go 5. It's just gonna work out this way, but it technically should be the other way around. It's fine. It does the same thing. So now you get divide, and okay, so actually, this is weird. The 15, the 5. Okay, so let's do it. All right, so we do 4, 13. Once we get a 5, what happens is actually, okay. No. Okay. So every time we get a number, it gets pushed down. So we get a 4, then we get a 5. So this 4 gets pushed down here. This 5 gets here. And now we get a 13. So this 4 gets pushed up here. 5 gets pushed here. 13 is here. And now we get a division. And so we do 13 divided by 5. And it goes down to the previous end. So this would be 2 point something, but it gets reduced to 2. So now we basically, where would that go? Well, this is a plus. But this is a new operator. So these 2 get removed. And so this 4 goes here. And then the solution, which is 3, the 2, sorry, goes here. And then we get a plus, and 4 plus 2, 6. This is not the way you actually solve the problem, but I was trying to like represent it nicely, but these problems are not helping. But you basically pick the last 2, and then you do an operation. And so a better way to represent it actually is if we remove all this. The solution, just to spoil it at this point, because it's going to be a better way to represent it, is going to be a stack. So you're going to have a stack. And this is where you're going to put your operands. So because we just take the last 2 expressions and then we do the operation with them, that's why we're using a stack, because the last in is the first out. First in, first out. This is LIFO, last in, first out. LIFO. Data structure. Push. And then pop. Yeah, so this is a LIFO structure, I believe. Stack. Yeah, so LIFO. The last in is the first out. First in, first out is the queue. So the last thing, it's like a cache. You take the most recent thing. Well, no, not like a cache. Ignore it. No, I'm getting confused. But you want the most recent things to like operate them. So that's why you use a stack, because in a queue, which is the other data structure, the first thing that comes in, it does it in order of like how old they are. So the things that were put into the data structure first are the ones that get addressed first. So if you go 1, 2, 3, then the way you would serve them is 1, 2, 3. In a stack is 1, 2, 3. And then you go 3, 2, 1. You go the other way around. So the last thing you put in is the first thing you take out. So that's why we're using it in this case. Now let's take the most complicated example, because it's going to be way easier to explain. Right here. Actually, let's make it smaller so it doesn't bother our stack here. So we're gonna put operands in the stack until we find an operator. So we put 10. We put we process 10. Now we go 6. Now we go 9. Now we go 3. And now we get a plus. So this is when we actually do something. So when we get an operator, we pop the most recent 2. So it would be 3 and 9. These get popped out and they become operands. So 3 goes here and 9 goes here. The order here matters. So the first one we pop out goes to the right. The second one we pop out goes to the left. And then we process it. So 9 plus 3 is going to be equal to 12. And now we can delete this. and we put this result back into the stack. So we put a 12 here. Now we get a minus 11. We put it here at the top. And now we get a multiplied. So we pop the most recent 2. So minus 11 goes to the right, and 12 goes to the left. And we multiply them. And 12 times minus 11 is going to be equal to minus 120 minus 132. Yeah? Yes, that makes sense. Okay. Minus 132. So now we remove these two, and then we put that back in. Minus 132 is now in the stack. And now we done the minus 11. So now we get this operation is done. We get our operator, which is multiplication. And now we pop these two. So minus 132 would go here. In this case, it doesn't matter because it's multiplication, but for division and subtraction, it does matter. And you put 6 here. And I'm not going to calculate this. I'm just going to do a little calculator on my phone. So 6 times minus 132 is minus 792. So this is going to be equal to minus 792. And now we do that. We put in minus 792 here. And now we divide. And now we're going to multiply after. So far. Oh, no. Okay, sorry. This actually, you do get the 6 and the minus 132. And this is actually division. I should have a pointer here. So we've already done all this bit. So now we're at division. So 6 divided by minus 132. And then, so 6 divided by minus 132, this is going to go to 0, basically. I believe is what I feel like it's most likely. So then we put that 0 here. And then we're going to multiply. So we get so this gets rid of that. We've done this one already too. Multiply, pop the two operators. 0 goes here, 10 goes here. 10 times 0 is 0. So now we just have a 0 here. Now we put in a 17 and a plus. 17 goes here, 0 goes here. This is equal to 17. And then a 5 and a plus. So now we get 5, 17 equals 22, basically. So that's the process. It's way easier to do with the stack, isn't it? Yeah, the trick to find the way to do it here, I mean, I've already done it, and which is how I know. But the trick to find out what data structure you need to use, oh god, is to realize that in reverse Polish notation, you're evaluating the most previous two operators. So if you want recency, if you care about like the most recently added, not the most, not the first one that was added, then use a stack, because a stack is like the most recent thing. If you care to like address elements in the order that they came in, then you do a queue. That's how you realize. So yeah, let's code it up. So this is gonna go in our stack slash, so the number of the problem, 150. And we paste that there. And then let's do that. And now here we're gonna do, so it's string tokens. That's fine. So let's do a stack of strings, I guess. and this is going to be our stack. And then for I don't know why are they address? Why is it a pointer? Oh, because you're passing the reference. Never mind. So I can just do string token in tokens. So right here, we're gonna do the following. So if this is gonna be an annoying and long expression, but bear with me. If token does not equal plus and token does not equal multiplication, that's not multiplication, that's multiplication. And then let's do it another 2 times. And token does not equal minus, and token does not equal divide. If it's not an operator, basically, what we're gonna do is we're gonna push it into a stack. So stack dot push our token. Else, if it's an operator, and this should always be a valid expression. It should always be a valid expression. So I'm not gonna double check if I have 2 operators, but int left is gonna be equal, actually right is gonna be equal to stack front, and then stack dot pop, and then, well, actually I have to convert it to an int. So it's gonna be that minus 0, or is there string to int C++? Stoy? I don't like using that. I hope this works. So we pop, and then int left operator is going to be equal to stack.front minus 0, and then stack.pop. And now we're going to do the operation. So switch, let's do a switch statement just to do something nice. Switch token case plus. If the case is plus, then we're gonna do stack.push. We want to convert this into a string again. So 0 plus 0 plus L plus R. And then we do 4 of these cases. If it's minus, do a minus here. This is going to be multiplication, and this is going to be division. And then this is going to be multiplication. Oh, this is going to be multiplication. And this is going to be division. I'm not going to do a default because I'm just going to assume it's correct. So we push whatever result it is. Actually, we need a break here because it's C++. Not that it's ever going to be 2 of these cases at the same time, but still, it's good practice. And now that we've assessed the 2 of them, we're done doing that. And at the end, we basically return stack.front, but we'll return that minus 0. Okay. I'm not sure about like the 0 plus whatever. Maybe it's better to do it this way. I don't know. but let's test it out. Line 11. Expression. Do I have to do that? No, because the errors. I don't think like that will fix it. I doubt it. What if I do this? How to do a multi-line if statement C++. See, you can just do that. I don't know what the error is. Well, in this one, I guess it does the plus the and in the line below. But I feel like that shouldn't matter. There's gotta be some other error. There's gotta be. Okay. Nope, that doesn't help. How do I do this? I would go like that, and then like that, and then VW, and then space. That's so much work. Or I guess I could just do and then oh, huh, I know why. It's because there's an extra and at the end. Dun, 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 dun. No member name front and stack. Is it top? I feel like it's top. Yeah, it's top. Okay. Front. Top. Okay. Cannot do this operation. Okay. Int. Well, how do you do an int to string C++? To string. That's boring. Okay. So this is gonna be stoy. And then just gonna look up zeros. And then this is gonna be to string, was it? Yeah. I don't BT. Oh, and then to string. CT. Oh, and then to string. And then just do that. Oh, do that. Stacked up top, but it's gonna be an stoy of that. Okay. Requires an expression of integer type. You can't do a switch with a. You can do a switch with a string? Not natively. You have to do an if else chain? Oh, this is so dumb. Okay. Stupid C++. Okay. So if token equals plus then. I mean, honestly, we can just delete this, do an equals, and then copy. Oh. Okay, I'm just gonna do this. Delete that. Delete the breaks. And then what's this connect to? Yep. And now we look up plus. This is going to be a minus. This is going to be a times. And then this is going to be division. And then we just format it. And then copy. Paste. Nice. Let's go. 7 milliseconds is not great, but it's fine. It works. There you go. Let's see my Python solution from November. If not an ops, append, pop both. Rest is none. If C is plus, minus, you do the multiplication, and then you append it. And then you pop. Easy. Well, today's problems were pretty easy. Okay, so tomorrow, I'm gonna be working again on the RAG project, learning some C Sharp. That's gonna be nice. And then on Wednesday, we're gonna do 2 more LeetCode problems, which are gonna be course schedule and implement try. Those are nice. I really like course schedule. I like the algorithm we use for it. So keep an eye out for that. If you're interested in more LeetCode content, keep an eye out for my building stuff streams. If you like that instead, like me just like building applications that I think are cool and for learning and fun for me to use. And then on Thursday, we're also gonna have another one of like the building a C# project ones. So it's gonna be today LeetCode, tomorrow build, Wednesday LeetCode, Thursday build. So that's what's looking out for the rest of the week. But we are done for today. I like doing LeetCode. I was trying. Okay, so for those of you that don't know like competitive programming, if you go to just the main LeetCode webpage, there's this thing called contests. What are contests? Contest is like a live simulation of let's say what it would be like to be in like a technical interview where you're like limited by time. That's the main thing. You're limited by time in the problems. So you, for this, like I'm very slow and I'm explaining through the whole approach and drawing it and whatever. For contest, you want to be fast. That's why I said not necessarily in an interview, because in an interview you don't want to be like just go really fast and then just finish your approach and it works, but you didn't explain your whole thought process. No, you don't want to do that for contests. You don't want to do that for your actual interview, but for contests, you're competing against other people to solve the problem first correctly. So you want to be as fast as possible. And these are live. They're questions that are normally like new. They're new questions you've never seen before in LeetCode. So it's not like you're gonna see questions from Grant 75 like flood fill or something like that. They're new questions. And you're trying to solve them as fast as possible to beat other people. I was looking to see if there was like any contests at like times that I stream, preferably not in the weekend because I like to keep my weekends free. There is not. Normally the contests are in the weekend. I looked here. I looked at Code Forces, which is another big platform. This is okay. So LeetCode is for like babies. Like this is like really easy, just for like technical interviews for jobs. code forces is like you're cracked at programming. Like these are like really hard math and algorithms problems, or you're gonna need algorithms that they're not gonna ask you for a technical interview, but the algorithms that are like studied in computer science, and like you should know them. So these are like they're divided by division, so like the higher the division, the easier it is, and there's like div 2, div 1. Div 2 is like one below the hardest level, and div 1 are like all the pros. Like Tourist is he's very famous. He's a grandmaster. Um, he's cracked. I wonder. He solves problems on like very specific times of the day, like the times of the week. But he solves a lot of them. 2010, 2011, 12, 13. Yeah, this guy's pretty good. But there's also contests here. If you go to contests, there's one, for example, on July 26th, which would be like Friday or Saturday at 10:35, and they last like 2 hours and a half. So they're kind of long. I mean, this one lasts 2 hours instead. But this one's for crack people. Div 1. So they're like live contests where you like solve the problem live and you try to beat everybody. So I was trying to look at that, but they don't really match my schedule, and like it's a very big time expenditure to like sit down for 2 hours and a half and the weekend. So maybe I will not do these, or maybe at some point. I'm not gonna close doors yet, but maybe at some point I'll get into it. But for now, I don't have any plans to do it. And also, I feel like contests, I mean, I haven't done them in a while, but like nowadays, it's not worth it because, well, if you're doing it to be like really competitive, because just a lot of people are just cheating with AI. Like they just put the problem in an AI thing and then just copy and paste the solution and they send it. Like if we see here, this is the person that got first. Rating. Okay, if we go to the contest itself, these are all the questions, and then standings. What's purple again? Purple is, so these guys probably did solve them pretty fast, but there's some people like that didn't solve all of them. So maybe there's not as many cheaters. I have to look into like what are they doing against cheaters. Actually, maybe let's look at that. What is Code Forces doing against AI cheaters? Remember plagiarism detections? Applied after rounds, you calculate your removal of cheaters from final leaderboards and can rely on some community flagging and reporting. Similar checkers to communicate against each other and known solutions. Calculate standings, community. So not really, it's hard to enforce. Yeah, so for like the competitiveness of it, probably not as good anymore because I feel like a lot of people cheat. But it's good for practice of like in like a real like time-bound environment to be able to solve the problems fast. You can also do virtual participation, which is like you do the contest already done, and then you just do it in your own time. So it's still like 2 hours length. You have to solve the problems, but like you're not competing with everybody. You're just like solving it in your own time, and then based on your time, you get put into like the virtual standings, I think. I don't know why that didn't work. Yeah, I have to log in to here and then whatever. I'm not gonna do that right now, but that's another option. So I could technically do one of those, but they're just kind of long. So I could plan for the future, but not now. Okay, just before I go, I'm gonna write comments for the solution. So, idea. Since reverse polish notation takes the two most recent operands, be it numbers or expressions, there should be a comma here. We will use a stack. This is because stacks give us the most recently added elements first, which matches our problem. We will add operands to the stack while we whenever we see them. If we see an operator, we pick the two top elements of the stack and do the operation on them. Then we put the result back into the stack. The solution will be the only element left in the stack at the end. Okay, very simple. And then our other problem was graph 133. And the idea for this is recursively create nodes, new nodes for the deep copy of the graph. However, only create nodes when they have not been created in the past. If we have already created the node we're trying to clone, return a reference to the previously created node instead of creating a new one. We check if we have already created a node by storing previously created nodes in an array. Yeah. Okay. And now we do get status, get add, period, get commit, add solutions from the console logs. This would be 13, I believe. Let's check. 13. My data is so structured. And now we do get push. Alright, solutions are up on the LeetCode. And that's good. Alright, thank you everybody for joining today. A little bit of a longer stream than we usually do, like an hour and 20 minutes, not too much longer, but I had fun explaining the problems. A little bit harder to explain this time. Like, I feel like they're not, I might not have done a very good job with the stack one. The graph one is kind of hard to explain, like the recursive solution, but I'm sure I could have done a better job at it. But that's part of why I do this, to also improve my explanations and stuff. But yeah, thank you guys for joining today and looking at me solve problems. And